Good morning, everyone. Good morning. Let's maybe wait a minute and start our lecture today. And yeah. Mhm.
Recording in progress.
So good morning, everyone. I hope you can see and hear me. Can you please drop a response through chat that you can see and listen me? Yes. Mhm. Thank you. Looks like we have good connections now, and we can start. So again, today we continue with the deformation of anisotropic laminated materials. And these type of materials, as we discussed, are extremely efficient and invaluable actually for aerospace applications. Yeah, so this is one of reasons we, consider them in such level of details. And today it's very important direction, subdirection, it's thermal deformation of composites, yes? And, you had, I believe, preliminary knowledge of thermal deformation, even from maybe middle school or even elementary school. We know under temperature, bodies and materials in general, yes, can deform using so-called thermal expansion phenomena, and it's widely used for a lot of applications, both as a advantage, but sometimes as a reasons to mitigate them. But in aerospace materials, it's highly important because many of materials are operate in really extremal situation, either too cold or too hot. Usually the second high temperature, it's much more typical challenge which we have, yes. So thermal deformation maybe is equally important as deformation under other type of loads. And today topic is what to do with it, how to analyze it, and how to take into consideration for your engineering design, optimization, and other type of assessment, yes. So outline for today's lecture is the following. We will start as typically we have with basics, and the basic is isotropic thermal deformation. In other words, we will refresh our memory on thermal expansion for traditional homogeneous isotropic materials. And again, to refresh our memory, isotropic materials are materials which have properties exactly the same in different orientation, or at least partially, yes? And anisotropic, it's usually like composite materials, fiber-reinforced materials, or some other highly efficient type of media. There, difference in properties in different directions can be used for our advantage, or again, as I mentioned, yes, can be a challenge which we need to take into account, yes. So the first bullet is isotropic thermal deformation. Next will be to move to anisotropic definition of thermal deformation. And here we will cover primarily two directions. One is what is the approach to analyze it. And the second maybe important consideration would be what is the fundamental difference between anisotropic and isotropic materials with respect to this type of phenomena, namely thermal deformation. And after that, we will move to generalization. We will apply this topic to laminated materials, yes. And again, we'll cover approach, general solution, and specific cases. And I would really, will pay attention on laminated material under thermal deformation, because in contrast with homogeneous, yes, materials, there are completely different phenomena, yes, namely there are so-called thermal stresses even without any applied load, yes, just because of difference in thermal properties in different layers or in different orientation, yes. And honestly, you know, those thermal stresses are as important as stresses and strains, of course, due to applied load, like more traditional, like forces and moments, because both together we could define a limit of structure, limit of material, and therefore, you know, criteria how to design them safely to avoid it. Yes. And as always, we will have at the end question and answers. And one maybe logistical comment you see at the bottom, I put a comment that sometime for questions regarding homework one will be available if needed. And the reason why, because do not forget, today is the deadline for homework one. Yes, today, again, Friday, deadline for homework one. You have full day till midnight, but I need, you know, to be sure it's submitted today. Yes, and as we discussed, do your best. And I will dedicate, maybe, as I mentioned, a little bit more time at the end of this lecture to go through questions and comments, if any. Yes. And I was speaking about that, was pleased how many people attended, you know, optional time on Wednesday this week. Yes. So again, looks like you're, you know, heavily involved with completion of this homework one. Yes. And again, as we discussed, homeworks, I consider homeworks as a major criteria of your knowledge. Yes. One thing is, you know, to be in lectures, to be familiar with theory, know the physics of phenomena, know the mathematical apparatus behind it. But as engineers, at the end of the day, you need to know how to apply it for actual calculation, for actual evaluations, assessments. Yes. So homeworks is kind of equally important as, you know, your knowledge. Yes. So as we discussed both parts, knowledge of basic physics, including mathematical description, but the second, skills and ability to apply it for solving practical problems. So again, this is a critical part of your curriculum. Please do your best to do it. Yes. So now coming back to content of our lecture, let's move to isotropic materials. Yes. So what you see here, yes, at my screen, yes, my screen, you see like in gray, like a representative material, piece of representative material. Yes. Let's assume for simplicity, it has like a rectangular shape. And let's assume we have some coordinate system, two-dimensional, 1 and 2. After that, let's assume this piece of material, it's heated, yes? And the temperature increase with the delta T. Again, at this moment, we're not discussing its positive increase, like the temperature moving from cold to hot, or negative, yes, because negative could be from a relatively hot temperature to relatively cold, yes. In the second scenario, delta T will be just negative, and in the first, it will be positive. So what we know with typical materials, if we have change in temperature, yes, it starts to expand. And under expansion, I mean like physical expansion, proportional to delta T, yes. So if it's delta T positive, it's expand. And if it's negative, cooling, it will be negative expansion, in other words, shrinking, yes. So here with this red dash rectangular around, I show a scenario of thermal expansion, yes. Again, it's obvious, yes, all of you should know it, not only from high school, but I believe from middle school, maybe even elementary school. So nothing new here, nothing should be new here, yes. But let's define it more accurately, because now you will see this accurate definition will be used as a bridge to make more generalized description of thermal deformation for anisotropic and laminated system. So again, let's assume we have coordinates 1 and 2. For isotropic materials, it does not matter if it's material orientation or arbitrary orientation, because isotropic materials don't have material orientation, yes. So let's assume 1 and 2 are given. And in this situation, we will have strain of expansion, epsilon 1 in orientation 1, and strain epsilon sub 2 as a strain in orientation 2, yes? Unrestricted thermal expansion, nothing more, yes? So based on our knowledge of physics, this strain will be directly proportional, you see my formula here, excuse me, to this difference in temperatures before and after, with coefficient of proportionality alpha, yes? And this alpha is usually called coefficients of thermal expansion. And sometimes the abbreviation CTE, yes? Usually people call it just CTE, to make life easier and to make it shorter, yes? So strain in one direction, direction 1 will be alpha multiplied to delta T. Strain in direction 2 will be alpha multiplied to delta T. And because alpha is the same in all directions, it's easy to see that strain in orientation 1 and strain in orientation 2 is the same. This is the reason I wrote here epsilon sub 2 is equivalent to epsilon 1, yes? It's not the end of the story, because another important consideration is, so if you have body and there is unrestricted expansion, there is no change of shape, yes? So shape, practically it's the same. Geometry will change. It became bigger or smaller depending on delta T, but there's no kind of deformation angular, yes? And again, if there are no other restriction, of course. So what I put here, that gamma sub 1, 2 is equal to 0, yes? In other words, from more practical kind of concept, yes, if I had a rectangular shape before and I heated it, it will expand into rectangular shape after, yes? If I had circular shape, heated it or cooled it, so it's expand and shrink into the same form, yes? It will be also circular. If I have ring, I heat it, yes, so it's expand, it will be ring with bigger radius, yes, and maybe with a difference in shape, yes? And actually, this phenomena of expansion used to be very convenient way in the previous industrial kind of needs, when you had to put some part into another, like in old times when people made guns and rifles and more severe type of weapons. Barrel was under extreme internal pressure, yes, during detonation of the powder, yes. So one of typical solution was, again, in old times, actually to have reinforcing ring around, yes. So to put the ring around was typical solution, to heat it, so it's expand, put to the barrel, and wait when under, ambient temperature, it shrink, keeping it together, yes? And again, nowadays also this technique is used for many applications. So again, as I mentioned, thermal deformation could be both negative thing, but also could be very positive, adventurous things, yes? So again, so far, nothing with respect to anisotropy or heterogeneous type of structure, nature of the structure, yes, but we will use exactly the same definition now when we want to move to anisotropic material, yes. So now we're at page 4. So let's compare it. So at the left side of the page, yes, I have exactly the same image and description we just discussed, but at the right side, yes, I have similar thermal deformation for anisotropic material now, yes? So let's start with material effect of material orientation first, and let's assume that orientation 1 and 2, yes, correlate with material orientation, yes? So a very simple interpretation physical would be that, for example, orientation 2 are orientation of fiber in fiber reinforced polymer matrix, a composite material, and epsilon sub 1 will be transversal direction, yes, primarily controlled by polymer, yes, and direction 2 will be primarily controlled by fibers in this case, yes. So obviously, thermal expansion properties of fibers are different than thermal expansion properties of polymer, yes? And because fibers are in orientation 2, like in this example, so here we would have properties primarily driven by CT of fibers. In an orientation 1, it will be thermal expansion primarily driven by polymer, yes? So again, it's very, reasonable to suggest that their coefficients of thermal expansion will be different in different direction, yes? This is the reason we're using alpha 1 to describe CT in orientation 1, and alpha 2 we're using to describe thermal expansion in orientation 2, yes? So what we see from here, what we see from this example, yes, if we consider deformation material coordinate system, so 2 and 1 correlate with material orientation, I see with my cursor, we had a rectangular piece of material, we heated it, it expanded, yes, but shape also will be rectangular after deformation, yes. So the only difference would be that strains in both orientation will be different, yes? Epsilon sum 1, strain orientation 1 will be still proportional to delta t, but now we need to multiply to alpha 1, and alpha 1 is CT in orientation 1, yes? Epsilon sub 2, again, will be proportional to delta t, range of temperatures, and multiply to alpha 2, and alpha 2 is actually what? A CT in orientation 2, yes? And at this moment, we are not talking about how to measure alpha 1 and alpha 2. We'll have a special lecture on experimental methods, and we will discuss it in detail. At this moment, we assume, okay, someone did test and gave you properties in both directions, yes? And actually, in material specification for different materials, yes, those properties are usually available. Another question, how much you can trust them, yes? But, anyway, those considered are classical or typical minimum for material characterization, yes? So again, we have epsilon sub 1 and epsilon sub 2 are not equal to each other, but also with respect to angle, yes, we would not expect any shear. Why? Because we still consider material orientation in as directions for expansion. So 1 and 2 are both material orientations, and those are orientations for consideration of expansion strains, yes? Any questions so far? Because this is one of critical things, that anisotropic materials will have different CT in different directions, yes? And second important comment, usually those properties, again, are defined in material orientation, similar to stiffness. You remember when we discussed stiffness, yes, usually, and I provide you with table of properties for your homework 1. All data they're given in material orientation kind of coordinates, yes, similar with thermal expansion, yes. So again, we have different alpha 1, alpha 2, and we don't have shear unless there is orientation the same as material directions, yes? So now what to do with this information, yes? And as we discussed, matrix definition is extremely convenient for analysis of anisotropic media, including both homogeneous and heterogeneous. So let's rewrite exactly the same set of those equations, in matrix form, yes? So we know already, actually here I need to put like 1 here, I forgot it should be 2. Yeah, thank you. So what we have here, we have matrix, one-dimensional matrix or vector of strain, epsilon sub 1, consists again of all those 3 components at the left here. And at the right, what we have matrix of thermal expansion coefficients for all directions. It again will be one-dimensional matrix or vector consisting alpha 1, alpha 2, and for gamma we just put 0 because something should be here. Something should be here, and this one-dimensional matrix or vector should be multiplied by scalar delta t. Yes, delta t as a range, excuse me, as a range of temperature. So this matrix equation can be written as is shown at the bottom. Matrix epsilon 1 is equal matrix alpha 1 multiplied to delta t. Yes. So exactly the same set of equations, but just written in matrix form. Yes. But now you will see why it's so helpful, because now we say, aha, if we can define in one orientation, we're smart enough have to recalculate properties in other orientations. It's exactly what you did or continue to do with homework 1 and what we did before with stiffness. So exactly the same logical approach. Yes. So you see, we're moving from simple to more complex, just increasing level of complexity, but logic, physical logic, practically the same. It's just mathematical apparatus became a little bit more sophisticated. Yes. And again, if we're using matrix form, it's, practically the same as scalar. Yes. Just with, from the viewpoint of description and for convenience of for programming, for numerical assessment. So now let's go to next level. Consider thermal strains for any orientations, any potential orientation. Yes. So now at page 6. So let's consider piece of anisotropic material shown as a right. Yes. We have arbitrary coordinate system X and Y. And we know material orientation 1 and 2 is not the same as coordinate X and Y. An angle between them is defined by angle theta, yes? So similar to stiffness, yes, we rotate one coordinate system to another, yes? So the question would be the following, yes? If you know thermal expansion in coordinates 1 and 2, what would be similar properties in coordinate system X and Y? Yes, very straightforward, very practical question. Actually, this slide will answer this question. So what we are doing now, first of all, at the very beginning, what you see my left side, let's rewrite equation for transformation of strains. Yes, we already know it from our previous lecture, and we know that correlation between strain in coordinate system 1 and 2, defined as a vector epsilon sum 1, directly proportional to strain in coordinate system X and Y, defined as epsilon sub X with matrix T2, yes, and matrix T2 is transformation matrix, which is what? A function of this angle theta, yes? So matrix T2 exactly the same matrix what you use in stiffness analysis when you need to recalculate stiffness, yes, stiffness of anisotropic material in one coordinate system to another, yes? So it's exactly the same matrix T2. And in general case, this matrix could have size 6 by 6, and if we consider more simple two-dimensional case, like in plane, it will be reduced into two-dimensional case with 3 by 3 constant, yes? So again, exactly the same what you had with analysis of stiffness in different coordinate systems, yes? So these so far have nothing to do with thermal expansion. But next step, yes, let me add here, shows how we can relatively easy calculate thermal expansion in any other orientations, in this case X and Y, yes? So what we are doing, excuse me, what we are doing, see, this is a first equation, yes? So this is a first equation exactly the same as we had at the top with respect to transformation of strains, yes? Now, from previous slide, we know that epsilon sub 1 can be defined as matrix, unit matrix, alpha sub 1 multiplied to scalar delta t, yes? This was, again, to repeat what we had, this equation, yes, this equation at the bottom, we say, okay, we know how to define epsilon1 as a function of delta t, yes? So now what we can do, instead of epsilon1 here, yes, we are putting this equation, yes, instead of epsilon1, we are putting this equation, yes. So we're putting matrix T2 transformation multiply 2x, and we are receiving this next level of equation. Yes, again, we substitute one to another. And eventually our interest in epsilon x. So what we need to do, we need to remove matrix T2, yes? So what we are doing, we multiply both left and right side to inverse matrix T2, yes? So what I'm doing here, if I multiply here inverse matrix T2, inverse matrix T2 multiplied T2 will give me unit matrix, so I don't need to show it. And now at the right side, I have inverse matrix T2, yes? So actually what we will receive eventually, we are receiving this type of equation. So strain in coordinate x and y, define my matrix epsilon x, is product inverse matrix T2 multiply to original matrix alpha 1 and multiply to delta t, yes? So what I'm doing now, I'm defining product of those two matrices as alpha sub x, yes, why? Because we still have the same factor delta t, and this product will be defined as inverse matrix T2 multiplied to matrix alpha 1, and if I multiply to delta t, I'm receiving strain, and without delta t, I'm receiving matrix, what's shown in this red box. It actually would be unidirectional matrix or vector of coefficients of thermal expansion for isotropic material in any coordinate system. Yes, in any coordinate system. Yes, because why in any? Because T2 is a function of this angle. You're changing angle. Constant in this matrix also will change, and you are able to calculate thermal expansion coefficient again in any excuse me, in any coordinate system. Yes, any questions here so far? Because from here we are moving to the next level, yes, and very important practical consideration, yes. So there are, here I put in more kind of explicit definition. So alpha sub 1, as we saw already, it's like has three components, alpha 1, 1, alpha 2, 2, 0, yes. However, if you calculate alpha sub x, you need to multiply to matrix 3 by 3 here. You will actually receive all those three components. There'll be alpha xx, alpha yy, but also you will have so-called shear component, alpha sub xy, yes? It's just pure mathematics, because now you have, for T2, you have many non-zero components, cosine, sine, etc., yes? So from here, we can draw very important conclusion, that number one, what you see here, if original materials alpha 1, for original materials alpha 1, 1, it's not equal to alpha 2, 2, so we have anisotropy of thermal properties, so we will have anisotropy of those properties in any coordinate system, yeah, or almost in any coordinate, but say in some cases we can fix it to have the same actually, yes, but in general alpha sub xx, it's not, it would be equal to alpha yy in general, yes. And the second very important bullet is we will have some kind of shear, yes, because, even if your material original has, alpha 1, 2 equals 0, after rotation, you will have shear, yes, so it's pure math, and here we have a very simple proof for that, yes. Why it's important? Why it's so important? Let me show you the next slide, and show you the thermal expansion of anisotropic material. Now it's, nothing to do with isotropy and isotropy, both of them are anisotropic, but what you see at the left, It's actually the same anisotropic material, but consider it along material orientation, yes? So if it was rectangular, after deformation also will be rectangular. Shape the same. The strengths in different direction are different, of course, but shape is the same. However, what you see at the right, yes, if we have the same piece of material, but with the oriented, material direction, yes, under certain angle, and we apply heat, yes, so this is the same rectangular piece, also deform differently in the horizontal direction, deform differently in vertical direction, but most important, it start also to shear, yes, just start to shear, yes. And actually, it's a very, very important phenomena for aerospace application. It's super important, but also for your practical, yes. I don't know, you pay attention, like with plywood sometimes, yes, under time, upon heating, but usually upon kind of absorption of humidity or moisture, yes, it starts to buckle, yes. Actually, this effect, because in plywood, you have different layers oriented under different angles, yes, and each angle try to shear in different orientation, and because of that, it could influence deformation. So it's not only that, but it also depends on stacking through thickness, which we will discuss in follow lecture, yes. But bottom line, the thermal expansion of anisotropic material in general is quite different than thermal expansion of isotropic, not only quantitatively, but also qualitatively, because now we have completely different phenomena or mutual shear. So again, now imagine you have system plus alpha minus alpha. You heat it, yes. So one guy try to rotate in one orientation, another guy trying to rotate in opposite orientation. We have to rotate to deform together because the same system. And as a result, now we have a huge shear between them, yes. So if adhesion between those two layers are relatively weak, so boom, immediately reason for damage, yes, immediately reason for damage. And in isotropic materials, it wouldn't be the case. And if we would have again, like 0.90 material, you see my hands, you will expand it, yes, there will be no shear as well, yes, because everything will be rectangular after that. But for plus minus, and this is very kind of common case, of course, yes, those shear components between layers are usually major troublemaker, and we will discuss interlaminar damage in follow-up lecture when we go to strength analysis and damage tolerance analysis. But at least, even kind of qualitatively, you can hopefully visualize why it happens, yes. And we'll speak about it more in details in future, but sometimes when you drive highway, you see like pieces of threads from tires. Actually, it's the same phenomenon, actually, yes. But we will speak about it more in details. Again, it's trying to this plus minus orientation, trying to move back and forward. It became fatigue, and interface between eventually could damage, yes. So again, a lot of very important considerations. So, ladies and gentlemen, any questions, comments so far before we move to laminated analysis? Because laminated analysis will be with a lot of math in addition to physics. So I want to be sure, thermal deformation for homogeneous body, but anisotropic, it's captured very well, yes? So actually, I would say major conclusion is here, yes? Major conclusion is here that if we know thermal properties in one orientation, for example, material properties, we can recalculate material thermal properties in other orientation, XY. And also we can do in opposite, actually, yes? So if we know alpha XX, alpha YY, and alpha X sub Y, we can recalculate those properties. But the challenge is sometimes it's very difficult to measure this angle. So usually people work in this direction. First, measure alpha 1,1, alpha 2,2, and after that you can calculate everything like what is. Yes. So I don't see any questions. and equations. And now we are moving to, let's go back to the thermal deformation of laminated system, better to say. We'll consider approach, general solution, and specific case. So I would like to ask you, please pay attention. It will be a lot of math here. Very straightforward math, so it will be relatively easy to follow because it's quite similar to what we had with stiffness analysis. So don't be confused with equations, which are very quite simple, because we follow exactly the same logic as we had with stiffness analysis of laminated system. But before doing that, let's refresh our memory. And go back to definition of laminated system. So how it looks like, what you see at the left side, we have package of number of layers, start from 1 to capital K. And my apologies, in equations I showed here, I use capital N, but it's the same actual logic, unlimited number of, but finite number of those layers, Now, each layer here, it's shown at the right, could have different orientation defined by angle theta, but each layer could have individual layers, so this is the reason called theta sub k. Also, it could have different thickness, defined h sub k, but also each layer could have different stiffness, different stiffness. So this package is kind of defined here. And if it's two-dimensional loading case, we have also applied forces per unit length. It will be n sub xx, n sub yy, and shear component n sub xy. Exactly the same which we discussed with stiffness analysis. However, the difference would be we will also have different thermal expansion coefficient for each layer, and also we'll have delta T, which entire package will expand as a function of applied thermal load. And sometimes in the paper or in discussion, people call it thermal load, So again, it's not like load what we traditionally define as a forces at a moment, but still it's a factor which could generate stresses, strain, and what is the most critical, could generate damage or failure. So it's this is a kind of explanation why something's called thermal load. So this is two-dimensional case of laminated system. So let's go to the next slide. This is exactly the same laminated package, but under three-dimensional case when we have also moments. So we have moment x sub xx, moment sub yy, and shear or twisting, better to say, moment sub xy. So how twisting work? You see my hands, one side it rotate in one orientation, another it's rotating opposite orientation, providing twist between them. So this 3D case with moments. Okay, let's see. It looks like there is a question. This one, This one or this one? Or this one? You can use verbal, you can say verbal, this one. So again, it's exactly the same what we discussed with our stiffness analysis, and we are not to take in consideration thermal expansion yet, but from here, we are moving now, to consideration of thermal expansion. And again, I probably, if I have time, I'll rewrite those equations more accurate format, but actually it will be exactly the same equation, just maybe written more accurately. So remember, when we discussed, deformation of laminated package, we say, okay, strain in coordinate system xy as a function of z, it's proportional, you see my cursor, strains as a neutral position, define strain sub 0, and proportional plus component proportional to curvatures, kappas, curvatures, but multiply to z. If z is the center, there is no curvature. As soon as you are moving up or down, effect of curvature will be bigger, So for positive z, we'll have extra strain. For negative z, we'll have minus strain. So these first two components are exactly the same what we discussed in analysis of stiffness of laminate system. But now we're adding extra component of thermal expansion. So we have delta T multiplied to this vector, delta X, of alpha sub X, alpha sub Y, alpha sub XY. And again, here I had to use XX, YY, so this reason I'll probably clean it. But again, sometimes it's used in tensor form, sometimes in matrix form. Here, I did not use tensor form for simplicity, yes, show it. But you know how to define it. So this guy, this component, it's actually what we calculated here, yes? So if we know orientation XY, and we know material orientation 1, 2 defined by angle alpha, for each ply, for each layer, we can calculate those properties, alpha sub X, yes, which are defined by this like one-dimensional matrix with 3 components here. So exactly the same. But point is, these those components will be different for different layers, for different plies, whenever words we're using. Yes. So now we're saying, okay, if we know strains, we can probably calculate stresses, yes, because we know if we multiply strains, and this entire portion is a strains, multiply to stiffness matrix of specific layer, what would you consider? We can calculate stress, yes? It's Hooke's law, nothing more, yes? So here it's a stiffness matrix of a layer with number n, shown as a Q, sometimes we use as a C, again, similar with stiffness, sometimes Q, sometimes it's the same definition. But actually, we multiply stiffness matrix of each layer to strain, and this individual layer defined by this formula. So now we have this definition, yes? And finally, if we define strain here as a matrix epsilon sub 0, curvature here is a matrix kappa, and this matrix is alpha, yes? So we will have finally this definition of stresses in layer n as a function of z, yes, as a function of z, yes, in this matrix form. In other words, stiffness matrix multiplied to this kind of summation, epsilon sub 0 plus z multiplied to curvature minus delta t multiplied alpha, yes. So this is actually Hooke's law, generalization of Hooke's law for, arbitrary case, when in addition to applied load, we have also thermal expansion defined by thermal load delta T, yes? So this is how we actually are using recalculation of alpha for different orientations, yes? So from here, if we know Hooke's law, and we know how to calculate all stress, what we're doing now, we're applying conditions for equilibrium, yes? But before going to equilibrium, let's see question. Yes, it's a very good question, I was hoping somebody would ask. It's a very good question. So why it's X? Why it's X? Why it's X? Because this guy is what we are looking for. So it's opposite, yes? So actually, let's forget for a second about curvature, yes? So actually, what we are talking about, epsilon sub 0 should be equal to strain because of load, plus this strain because of thermal expansion, yes? So if I would rewrite its original, it would be epsilon sub 0 is equal epsilon sub z plus this component, yes? And because we're interested in actual strain which we have in each layer, actually we need to put this component from left to the right, yes? So here we'll have minus. Excellent question. And actually it has very practical definition why to use it. And I have a special slide on that, because for example, you have piece of material restricted, there is no opportunity to move. If you heat it, yes, it will be under compression, yes. If you cool it, it will be under tension, yes. So depending what kind of boundary conditions you have, you can create like extra compression, extra tension, extra shear, actually extra bending, yes. But this sign is correct, yes, and this sign indicate that strain here, will be in opposite because epsilon sum 0 is fixed, yes, and this is what we're looking for. But very good question, very good question. I was hoping, this is the reason I actually highlighted it, yes, hoping, somebody would ask, really appreciate it, yes. So coming back to the logic of our analysis, we have stresses here as a function of stiffness, epsilon sub 0. It's a strain in neutral position bending. It's K or kappa Z position through thickness, but also now we have delta T. So what we're doing now we're going to equilibrium solution. What we're doing, what you see for equilibrium, if we summarize everything through thickness, yes, like all our stresses should be summarized through thickness, through dz, we will receive N. Yes, what is N? It's this kind of combined force through thickness. Let's go back. Combined force integrated through thickness. Yes, and similar here, if we integrate it, but also stress multiplied to Z position through neutral position Z, we will calculate also all those moments. It's actually how much it's bent with respect to neutral position. Yes, again, exactly the same what we did with stiffness analysis. Yes, so this is equilibrium condition for in-plane forces in matrix form. This is equilibrium condition for moments for three-dimensional case. They look quite similar, but here without Z, here with Z, yes. And of course, integration is going from lower side of laminated package up to upper, yes. This is the reason I put minus h/2 plus h/2, if it's symmetric. If not symmetric, it will be within, but again, through entire overall thickness h, yes. So if we integrate it, yes, we will receive this, equation which we had similar to with stiffness, yes. So let's forget for a second about this component, but this portion, yes, you see my cursor, yes, it's exactly what we had in previous lecture, not on Tuesday, but last Friday, what we called classical laminated theory, yes. So matrix N and matrix M are proportional to matrix strain and neutral position and bending with this matrix ABD, yes, ABD. This matrix is symmetric, and A is the in-plane stiffness, D is bending stiffness, and matrix beta show effect of imbalance between them, yes. So this portion, exactly the same what we had in classical laminate theory based on this integration, yes. But now we have additional component here. Why? Because we had, let me go back, because we had this guy. So this guy, if we integrate just this guy, yes, this component delta T multiplied to alpha and multiply to this stiffness, we will receive extra components. Let's call it N sub T and M sub T, and N sub T will be equal to this. Again, it's integration through entire thickness. Again, exactly the same approach. You have delta T multiplied to summation, each stiffness matrix for each layer, multiply to alpha for each layer, and multiply to thickness of each layer, yes? And for moments, again, similar format, delta T, multiply to summation for all layers, it will be a stiffness matrix, multiply to CTE matrix, and multiply, now instead of thickness, we position square, minus within square over 2. Why we have this? Because it's integral z dz. So integral z dz is equal to z square over 2, as we know from calculus, yes? So again, exactly the same approach for analysis, we just receiving 2 extra components, yes? And again, in slang, and sometimes, in engineering discussion, those components N sub T and M sub T called thermal loads, yes, thermal loads. Those are not loads, actually. It's just, function of delta T. But they could produce the same effect. They could generate stresses, strains, most important, they could produce additional risk for damage, yes. So this guy, this kind of equation in matrix format, it's called the generalized classical laminated theory to take into account thermal expansion, yes. So it's we added extra component here, yes. And some of you could ask, okay, what to do if delta T is not uniform through thickness? Yes, it's also kind of typical, not typical, but not unusual case with aerospace application. Like imagine like spacecraft, for example, or even aircraft. You have outside relatively cold, inside ambient temperature. So you have difference in temperatures through thickness, yes? So in this situation, what you will do, you will not use delta T outside of integration, but put delta T for each layer inside, yes? So it will be the same approach, but you will take into account the temperature for each layer also could be different, yes? Also would be different, especially for space applications, quite critical. And there are, special optimization kind of styles of thinking, how to avoid negative effects because of that, and how to actually maximize effect of it. Like many years ago, I had a project for satellite. It was like composite panel, big panel, yes, for satellite system. So actually it was like one side when you were in space, so it was close to minus 150 C, yes. An opposite side, because of sun, yes, could be heated up to plus 150 C, yes. So this is like a panel, you have gradient of temperature through thickness almost 300 C, so it could be like maybe close to approximately 600 degrees of Fahrenheit, yes. And it's huge, and because of that, the entire system could buckle, yes. If it start to buckle and bend, it will be, reasons for damage, but most important, it destroy accuracy of all this optical system. For optical system, geometrical tolerance is really super important. So actually what we did, what was what we proposed, to optimize structure, to make artificial imbalance. So even if you have gradient of temperature through thickness, it will not buckle actually, or buckle with very limited deformation. Yes. So again, if you know it, yes, you can kind of apply this knowledge with the, to optimize and to mitigate challenge. Yes. But again, we are not discussing your homework too will not be focused on delta T change through thickness, yes, but in general it will be the same approach. When you integrate here, delta T will not go outside the integral, but will be inside. So again, mathematically speaking, it's exactly the same, yes. They're the same, just with very minor modification, yes. So now from here, let's go to the next slide, and let's consider specific cases, yes. So one specific case, very specific, interesting case, when you have delta T is non-zero, so you have heating or cooling of system, but you have no other load. So vector n is 0 and vector m is 0. So no in-plane load, no any moments whenever bending or twisting. Just we apply delta T. So what we are doing, yes, we consider this equation. This is the same equation, but instead of n and m, in plane loads and bending load, we put 0 and 0. So exactly what we are doing here. I would say, okay, n and m equals 0. So what you have this portion actually, yes, equal to 0. And 0 could be also vector, yes, one-dimensional vector, like with 6 components here, yes. So now we have this guy minus this guy is equal 0. So what will be our next step? We will separate. We will put this guy to the left and this go to the right. Yes. So now we have this stiffness matrix ABD multiplied to epsilon sub k is equal to this matrix NT and MT. Yes. And because delta T is non-zero, so, matrix NT-MT in general case also non-zero, yes? So it's non-zero. And what we are doing now, we know how to calculate these guys. Again, let's go with this equation. It's based on your laminated package. You need to know stiffness of this package, stiffness of each layer, thickness of each layer, and alpha of each layer, and delta T, of course, yes? So based on those two equations, you can calculate component NTMT. So if you want to understand strains and bending, K, deformation, curvature, what you are doing, you multiply left side and right side to inverse matrix here, yes? Inverse multiply to original give you unit, you can ignore it. So now you have just epsilon sub-zero and curvature. And now you have inverse or compliance matrix of laminated package, ABD minus 1, but multiply to NT-MT, yes? So why it's so important? Why it's so important? So observation here is the following. If delta temperature is non-zero, NT and MT are also non-zero, so we always will have both strains in a neutral position, but also we could also have bending, depending on laminate, it's balanced or not, yes? And actually, if we want to calculate what would be effective thermal coefficient of thermal expansion for a laminated package, you can even go to the next level. You can consider case when just you have strain in neutral position. So you will have epsilon sub-zero is inverse matrix A when B is 0 multiplied to NT. And NT is what? As we see here, directly proportional to delta T, yes? So actually this is equation of how to calculate effective coefficient of thermal expansion for any laminated package. You just divided it by delta T, and here on the left side, instead of epsilon sub-zero, you will have all alphas. Alpha in orientation XX and alteration YY, and also shear, if any, XY, but for laminated package, yes. And similar, if you want to analyze how it's bent, yes, now you have this equation, because MT is non-zero. So now if in this situation you would have, kind of bending of the system again, assuming you have kind of, unbalanced system, yes? And again, example I gave you with plywood, when it starts to kind of buckle with temperature, with moisture, with absorption of moisture, it's exactly this phenomenon, yes? And we consider delta T, just thermal expansion, but if we will add component of moisture, it will be exactly the same mathematical apparatus, yes? And, we just need to know, coming back here, half strains, yes, half strains, no, not here, it's this one, yes, this one. Half strains are correlated with moisture, yes, or absorption of moisture, yes. So it will be, instead of delta T will be factor defined by moisture, and instead of alpha 1 will be matrix of proportionality, yes, proportional, but the same logic. But again, because moisture has much smaller effect than thermal deformation, I kind of move it from here, but I just want you to know. For you, you will be aware. So every time you see like material start to buckle, yes, originally was flat, start to buckle, it's exactly those type phenomenon we are talking about. And actually, it's a huge issue in fabrication of composite parts, because to fabricate them, for example, if we are using thermosets, polymers like epoxy, yes, what you have to do, you create like lay up, you put in the oven and you cure it under elevated temperature, yes? And upon curing, it became solid, you remove it, and of course, when it's moved from oven to ambient temperature and room temperature, it starts to cool, yes? And this funny situation could be, in oven it was flat, but when you move it and start to cool, it start to buckle, yes, start to buckle or even twist. Could be a really crazy shape, yes. So, it's a huge issue with respect to quality, and, to address it, what is needed to, it's like very, clear understanding how laminated materials deform, even without any applied load. No forces, no moment, but just because of change in temperature, this will be deformation. And again, in this situation, it's not like you have flat at room temperature, you heat it, start deform. It's exactly opposite. Originally, it was at elevated temperature. Just after fabrication, you remove to the room and it start boom, buckle, shear, etc. Yes, it's a huge issue in manufacturing of composite structure. Not huge, but relatively big, I would say. And to address it, people specifically modify design to be sure it's not happens. And if happens, it will be minimized. Yes. So this is what I wanted to share with you with respect to thermal deformation for both isotropic, anisotropic, and as a variant of anisotropic, laminated materials. Yes. So again, major takeaway is, it's thermal here. It's another component of load, what we did not have in more traditional isotropic and homogeneous materials. It's different component. And when we move to strength analysis, yes, we will discuss it in details. We could say, if during service we expect range of temperatures, it should be taken into account in both directions. How strength property and stiffness property change with temperature, but also, if there are additional stresses and strains affecting risk of failure. Yes. Okay, there we are. As I promised, I wanted to dedicate some time for homework 1. If there are any comments, yes. So we can use remaining part of our lecture for this type of, discussions. And again, the first asked question will be the first to receive answer. And again, as always, I put this presentation to Canvas, and I own you also 2 more presentations, yes, on lecture 8 and lecture 7, yes, regarding laminated analysis. So I hopefully put it today. I wanted to put it before, but wanted to make nicer equations, like here, yes, etc. But it took more time. So probably I'll see what I'll do. Maybe I'll use the same format, handwritten equation, or remake them. But you will have it during the weekend, no doubt about it. So reason I'm so focused on laminated theory, kind of keeping you abreast, yes, is that your homework 2 actually will be on laminated analysis. And on Tuesday, I plan to issue homework 2. And again, you will have 2 more weeks to work on that. But again, plan accordingly. This is the reason I want you to finish with homework 1 and have, time and room for working for homework 2. It's one rationale. But the second rationale, it would be logical for you to start to do homework 2 if you cannot complete homework 1, because homework 2, laminated analysis, will be heavily based on the first homework, yes, because you needed to kind of consider changing material orientations always, yes. So plan accordingly and be prepared on Tuesday to have assignments for homework 2, yes, laminated analysis. And otherwise, let's if you have any questions with respect to homework one. And if some of you don't have questions, I specifically kind of reserve some time. If you don't have questions, you're free to leave. I'll be here online anyway till the end of the class. Let's see, question. That's a graph. Yes.
Professor.
Yes.
Oh, sorry. Sorry, go ahead.
Let me answer first. Sorry. Let me answer this. Yes. So are the graphs and homework mandatory? Answer is yes. Yes. Free graphs, you're talking about free charts, but for each chart you will have free components. Yes, because for example, for strains E1, vector 1, you will have epsilon 1, 1, epsilon 2, 2, and gamma 1, 2. Yes, so each chart would have free components. Yes, so maybe it's not clear in your message. You're talking about free course in each chart, or how many charts. Ideally, I ask you to prepare 2 charts, strains in material orientations and stress in material orientation. But you know, I forgot that actually chart number 3 should be also included. It should be strains in coordinate X and Y. So if you will not have, it's not error because I forgot to ask it, but I would strongly encourage you to plot all 3 charts, yes. Vishwa, I believe I answered your question, yes. If not, don't be shy to type another question, yes. And for homework 1, let me see what is here. So for one, can you explain how to start with? Yeah, I can explain. Yeah, we can do it. And let's go back. For flowchart for variant, we start with finding X when X. Yeah. Okay, hi, Professor. Yes, okay. Yeah, so let me open. Let me open homework. Homework 1. Yeah. So homework 1, it's yeah, it's here. Yeah, can you see my screen, please?
No, we cannot.
Can you see my screen, please? Yes.
Yeah, we can see it now.
So this was homework 1, and question was regarding variant 1. Yes, so regarding variant 1 and variant 2, what is the difference between them? So remember when we discussed analysis, we kind of brainstorm what kind of ways could be for calculation. So again, let me make it a little bit bigger even. Yes. Yeah. So you have piece of material defined in coordinate system X and Y, yes? So in coordinate system X and Y, you have load conditions, yes? So this matrix for you is given, it's part of input, yes? So your problem is you need to calculate epsilon sub X, deformation of this piece of material coordinate X and Y, but also as a byproduct, you need to calculate stresses and strain in material coordinate system, yes? So there are, 2 ways to do it, yes? So one way, what we discussed, at least 2 ways, it could be more actually, yes? So variant 1 is the following way. So if you know sigma X and sigma Y, what you can do, you rotate and calculate strains, stresses in orientation 1 and 2. This was variant 1, yes? Now, if you know stresses is in orientation 1 and 2, you create a compliance matrix in material orientation. It's called S1, yes, and multiply S1 to sigma 1, and you will receive strains in material orientation, yes, strains in orientation 1 and 2, yes. And after that, as soon as you have information on strain 1, 2, you multiply to transformation matrix, and now you calculate strains in material coordinates X and Y. This was variant 1, yes, it's kind of follow this logic. Yes. However, in variant 2, you can do in opposite way. What you can do, so starting point is exactly the same. You have load condition. It's stresses sigma x and sigma y. Yes. So apply load condition. Then you calculate compliance matrix, but already in coordinate system x and y. Yes. And you had formula for that. Yes. So from here, you multiply matrix S sub x to matrix sigma x, and now you calculate directly what? Strains in coordinate system x and y. And from here, when you know strains x and y and gamma, of course, now multiply to corresponding transformation matrix, you call the epsilon sub 1. Yes. So point was the following. Yes, the same physics, but different kind of sequence of steps. However, if you are using variant 1 or variant 2, calculation of epsilon x here and epsilon sub x here should be the same. And similar calculation of strain epsilon sum 1 here and epsilon sum 1 here should be exactly the same. Yes. So this was the reason. When we went through example. Let me show you. Went through example. I suggested for you to create a formula. What was it? 1 second. Example. 1 second, let me find it quickly. What I showed you last time. 1 second, let me find it. My folders. Oh, okay, it's here. Let me see. Where is it? I even put it, I believe I even put it into Canvas. 1 second here. Okay. Okay, it's here. Okay, it's here. Yeah, I had a separate folder. Yeah, can you see my screen, please? Okay. Yeah, I put in a separate folder. You remember when we discussed, yes, this was a point. So when you have summary, yes, of your prediction, one will be on variant 1, and another will be for variant 2. But for variant 2, you don't need to calculate max value and mean value. Yes, so for comparison of variants, you will have one. Here, this line will be similar cursor will be, for example, variant 1. The second line will be variant 2. And if all of them are the same, you could say bingo. Yes, it's done correctly. Yes. So this was a kind of comment on variant 2. Is it clear, or you still have questions here?
Professor, I had a quick question.
Go ahead.
Can you please go back to the table for 1 second? At the max and min value.
Yeah. Yep.
So over here, it asks for the max and min values of sigma x, sigma y, and tau x.
Yeah.
So aren't those the given values?
Yeah. Those are the same. This portion just ignore. because
Okay.
the loads will not change with because it's given load. Yes, it was my misprint. Good catch. Yes, good catch.
Okay.
Yes.
And
Or,
I had
or
another
you can use, or if you want, you just put the same values, you
same
know.
values.
Yeah,
And
yeah.
are we also supposed to put the angle of theta at which the max and min values occur?
If you want, you can do, yeah, it is good idea. It's a good idea. You will say, because usually what I expect, you know, I would expect for you to have this type of charts. Yes, so you could say,
Yeah.
just for example, minimum, it's maximum. Actually, it's a good idea. Yeah. It's not required, but it's definitely it's good sign how you know systematically you work with that. Yeah, very good idea. I would.
All right. And
I
I had one
I would
last.
I would suggest here for you, you know, and for other, just add extra line, yes, here. So you put
Mhm.
max value, but also you put angle of max value. It's have mean value, and next line would be angle of mean value. Very good suggestion. Very good suggestion. Yes.
Okay.
For the next class, if I'll teach it, you know, I will include into, you know, assignment. Yeah. It's a very good point. Very good point. Yeah.
And Professor, I had one last question.
Yeah.
So we need 3 charts or 2 charts?
Yeah. So I put in assignment 2 charts, yes.
Yeah.
And I definitely had to put 3. So if you put 2, it would be fine. But anyway, you will calculate information for all 3. Yeah. So I would
Okay. Mhm.
strongly suggest kind of, you know, to a little bit push envelope and to have, here you have strain as a function of angle, yes. Here you have like stress as a function of angle, but you could also put strain in material coordinates as a function of angle, yeah. So I would strongly suggest, you know, if you put 2, it will be fine, but
Mhm.
you know, kind of good practice would be 3, because anyway you have this information already in your calculations, yes.
So the three graphs you would need is the graphs for sigma
This
y,
one,
which is
this
in
was
the
this one
yeah.
for this part, yes. Strain in material orientation, yes.
Yes.
Now this would be stresses is in material orientation, and
Yes.
this would be portion, you know, strains in arbitrary material, an
Okay.
excellent kind of given, yes. It would be very good, very systematic kind of, you know. The reason I forgot about this, because usually what people need, we need strain in material, stress in material to make judgment regarding strength. Yes, usually this is kind of critical, but this is also very important information. So, you know, it's and again, in general, don't be shy to put extra information in your presentation, because it could kind of counterbalance if you forgot something, you know, to do, but you add something extra. I would say, okay, minus with plus will give me, you know, kind of balance. Yes. So, and again, PowerPoint, it's cheap, you know, you just put extra slides. Analysis, it's cheap. Excel, or, you know, MATLAB or C++ is doing it for you. So it's just question of kind of dedication. It's not extra work, actually, I would say. Yes, just dedication. And if I would be you, you know, if I would be you, it's interesting to see, you know, you could see, you know, how with the angle actually your picture completely changed. Like, for example, you know, a small angle, you have, you know, this component YY, it's bigger than component XX, yes. When you are around 40, they're about the same, yes. But when you moved here, it became opposite. Yes, blue became bigger than this. Yes. So what it will tell you, let's show better with stresses. Is what it will tell you is it's actually, you know, have to design, because you have unidirectional material and you want your fibers to work. So ideally, you want for fiber for 111 to have maximum, yes, and for opposite orientation 2 or 1 2, you want to have minimum, yeah. So you could say, see, blue is almost kind of, I can't say constant, but relatively small variation, yes, from here to here. But green guy is moving with huge variation. The green guy is shear, and shear it's troublemaker, yes. So your conclusion would be, you don't need to make this conclusion, but after homework 3 with strength analysis, you would say, aha, I really want to have smaller stress, so my orientation would be somewhere here, yes? So here we have smallest shear, relatively small transversal, and sigma 1 will be still about the same, yes, something like that, yes? And we will discuss optimization in more details, but those are, when we discuss conclusions, yes, this I would expect from you, kind of, to apply your kind of, critical thinking, how you can interpret those results and how to try to use for some benefits or for mitigation of some challenges, yes? This is a logic. So answering your question, if you have 2 charts, that's fine, but the more you have, the better, yes? If you even produce optimization and say, hey, I really kind of optimize with such, it's not only max and min, but because combination of them, that would be again extra plus for you,
Got it.
Yeah,
Thank
kind of. It's a little bit longer answer on your short question, but it's a lot of kind of learning process. It's not just to do results, send to professor and forget about it, but also a little bit to see what to do with that. Yes, what to do with that. Yes. And actually, it will help you with exams too. Because exam will have those theoretical questions, how to use those results, why, etc. Yes. And again, hopefully you see the logic in our homeworks, each after another. But when you see homework 2, homework 3, homework 4, you see like each homework is based on understanding of previous one. Yes. So kind of with each of them, kind of your skills will grow. Hopefully. Yes. Yeah. Okay. Very good. So I missed some of question in chat. So for homework, yeah. So we started like, I believe it was thermal, yeah, minus we answered this, discuss it. So the graphs on homework mandatory, answer is yes. Discuss how many, we also discuss it. For homework 1, can you explain how to start variant 2? We just discussed it, yes. I believe it was kind of sufficient answer, yes. Yes, hopefully. If not, we still have time, we can discuss again. So Pratik asked a question for the flowchart for variant 2. Start fun again. Yeah, that's correct. That's correct. So for flow variant 2, it's kind of opposite. So you calculate matrix S sub x already in rotated coordinate system. And you directly calculate strain in rotated coordinate system. But after that, you go back and calculate strain in material orientation. Yeah. Exactly. Hi, Professor. Here's no question, but probably, yeah, after that. So I left you an email on Wednesday. I did not check email yet. I am planning to do it after the class during the day, yes. So, William, I will respond during the day, yes. But for me, day could be late evening too, so it could be after 5. Because I have day work too, So if SX for variant 2, check it, I do not want to answer for you yes or no. I want you to go through, our lecture, through literature and check it, yes. But you have very, very clear formula for S sub X, yes. I want you to check it, yes. In the control validation, are we just comparing result? Yes. So what you do, Rishi asked a question, in the control validation, are we just comparing the result between variant 1 and 2? Yes, that's correct. So you calculate epsilon sub x and epsilon sub y. Variant 1, you calculate epsilon 1 and epsilon sub x. In variant 2, you compare them, and theoretically results will be 100% the same, yes? If you're the same, you could say, aha, at least one check mark is satisfied. It's not the only check mark, but at least one is satisfied, yes? So it's a very good check. Answer is yes. And again, you can use like a table format similar to what we just discussed, similar something to something like that, like variant one line, variant two another line. So it's easy to see all numbers correlate and put conclusion at the bottom. The results are the same, so it's indicate the calculations are correct. Yes. Okay, let's see. So for the problem statement, we can just copy and paste. Yeah, it's approximately, Pratik asked for the problem statement, but you need to maybe add some wording, yes, because I put like in bold format to describe. You could say objective of this work is to calculate such and such outputs when we have such and such input. Yeah, so roughly the same. And here, please be sure you will add graphic. Yes, like you can copy and paste my cartoon or you can plot your cartoon, but to emphasize what kind of coordinate system we're talking about, X, Y, 1, 2, rotate in one orientation or another orientation. So be sure you include some figure into cartoon, into problem statement slide. Yes. What do you mean by strain? Yeah. It's a very good question. Very good question. What do you mean by strain in percentage? So for strain, it's quite normal to discuss it in percentage. So for example, like people like myself, you tell me strains are 0.5% or 0.1% or 1%, has huge meaning, yes, because I know if it's close to 1%, it's bad. It's already close to damage, yes. So when you calculate like 0.00535 for free, or when I need to mentally another engineer to recalculate how much it is, yes. But percentage, it's very convenient way to estimate strains, because we know approximately between 1 and 2%, we are in bad situation. It's close to failure, yes. So usually, now we say, okay, depending on safety margin, how much it should be done. So percentage is extremely convenient way to kind of visualize it. So I would strongly recommend you to use percentage. But if you will not use percentage, it will not be an error. But percentage, it's very convenient to do. Yes. Okay. I believe I answered your question. Yes. Yes, with very percentage. What do we have to include for the control part of assignment? We just discussed like table, yes, line with variant one, line with variant two, and if we are okay, it's the same. You could put conclusion at the bottom. Both variants produce exactly the same results. Boom, one conclusion, one line. Ryan, I believe I answered your question. Yes. Can we attach our Excel file in the submission? Yeah, you have to. So one was, we discussed you include print screen of your Excel file, yes, into your presentation. And if you want, you can include original Excel. So usually what I do, I compare your predictions with my answers. I already calculate all answers for homework. So I say, okay, you calculate this, I calculate that, let's compare. If results are the same, I don't need actually to go into details of your Excel spreadsheet, yes? But if not, we can discuss with you separately, during this consulting and see, well, what was the problem, yes? I would expect you, of course, to find the problem, yes? But, short answer is definitely you can include, please include Excel file, but also do not forget to make print screen in your PowerPoint presentation, yes? So it's kind of would be print screen is mandatory, and Excel files I would strongly recommend to include, yes? That would be perfectly fine. So I don't see any, okay. One more question from George. The maximum value are for angles between 0 and 90. Correct, yes, answer is yes. Answer is yes. Okay, any additional questions, comments? Okay, so both of us, you and me, we have homework for you to complete and submit to Canvas today. Homework one, and for me, it's put today's presentation and two previous lecture to Canvas. I believe I will do it through the weekend, yes? And the next week will be dedicated checking your homework. So do not expect my answer immediately. Yes. So my response will be through maybe through the entire week. Yes. And you know how to use Canvas. I will put like comment and grade. So for homework 1, maximum it's 15 points. So everything fine, you will see 15 points. Somebody have extra, maybe I will add a couple of points more, and vice versa. If something is missing, again, it will be opportunity to, grade it accordingly. Yes? But again, try to complete it today. Yeah, I cannot be even more, kind of specific about it. Okay, very good. There is no question, 10 already. So have a wonderful evening, day, and coming weekend, and see you on Tuesday. Yes. Bye. Thank you. Bye.